Hi guys. Last time we were talking about pressure after density. Yeah, we started this section with how many of you are there? In the past few lessons, we have been looking at density, the properties of matter. No? First, we looked at density, how to find density. That means for a regular shape, you calculate the volume. For example, for a cube, it's length times width times height. And for a cylinder, it's pi r square times the height and so on. The formula most probably will be given. Then mass over volume, after that gives you the density. Now, on the other hand, if the object is an irregular object like a stone or something, we use the measuring cylinder and measure the liquid level before and after adding the stone. Then the difference between the volumes is the volume of this object. That's a clever way of measuring the volume. After that, you measure the mass of the rock, and mass or volume is density. Then for liquids, we figured out that measuring volume of a liquid is very easy, just in a measuring cylinder. But measuring mass is the thing. No? So for that, after placing this measuring cylinder on top, you take the reading, right? The first reading. Then after adding 100 milliliters of liquid, you can take the second reading. So the difference in reading is the mass of that liquid. So again, you run a mass or volume calculation. Then on Friday's lesson, we have discussed about pressure. Pressure you learned in year 9, it's the force per unit area. No? It's what makes things sink into another thing. Yeah, for example, if you're walking on hard ground versus muddy ground, it sinks into the muddy ground because, like in the muddy ground situation, the pressure exerted is more than that flow can bear. Then, like, we also see a stark difference in the, now, in many situations, pressure has this equation: pressure equals force over area. So it's superbly applicable in the case of a thumbtack. Imagine now if you are holding a thumbtack like this, you know that small things they used to pin on the board. If you're holding it like this, when you press, right? If you press this, you will feel pain here, but not here, because here the contact area is large. Therefore, the pressure is less. Now, there is a demonstration of this pressure being, inversely proportional to area using nails and a balloon, right? I think we should take a small look at that. How is it possible? 1 second. Okay. Yeah, I'm going to share the screen. Hold on. By the way, now, do you have any questions about pressure?
Right, so we have to define pressure. When you think of pressure, you think of weather pressure, that kind of. Pressure is when two things come in contact with one another, and that force exerted over that area. So, for example, if you take the nail, go ahead and hang on to the nail, and if we take the balloon, if we put the balloon on that nail right there, all of the pressure of that is pushed right there on that, and so it's no wonder that it pops. Right. Even if you did two nails, here, hang on to two nails like that, we're distributing over two nails, and still we have no problem at all. So here's what teachers can kind of make, or parents can make. Like they're going to go out today and just going to make it. Here is a board that has little tiny holes in it, and what you do is it's just a Sunday afternoon. You sit there. What else do you have to do? Sure, right? Drill. Right. So there you go. So now there's 100 nails that are sitting in there, and this sits here. Okay, you got it. And now let's do this one. The balloon goes on top like this. All right. Okay. And now, so that your hand doesn't get hurt, now the board goes on top. Kind of. I got the feeling of what's going to happen here. You think you know what's going to happen? I think that it's going to come down. It'll be perfect right there. Okay. All right. So now watch this. Take your hand and start to push down, and take a look at what happens. All of that weight and that force is being distributed over the entire thing that's there. So we have 100 nails. You can actually look inside and see them poking up inside. That's a tremendous amount of pressure. Can you see that right inside the balloon being pushed up literally inside? Any one nail would pop. They keep going down, keep pressing, keep pressing. See, now that's a lot of see, that's a lot of pressure. A lot of pressure. Yeah. Now I want you to get on the bed of nails. So just kind of climb up and just sit there, just like this.
So that's a quite interesting difference. So, okay, do you have any questions about solid pressure? I mean, it's a relatively straightforward thing. Only thing you have to be careful about is when you have multiple tires or multiple legged animals. For example, if you are given the area, contact area. By the way, year 9, you may have learned it as surface area. That's not correct. Okay. Contact area is that is this pressure equals force over contact area. Surface area means like, everything. So, yeah. Any questions about solid pressure? Tivanka or Agilash? No? Hold on, please. Give me a second. Sorry. Then we'll go to liquid pressure if you don't have any questions. So in liquid pressure, we studied that the pressure is equal to all right. So the pressure is equal to height times density times gravity. So the deeper you go inside the surface, the more pressure you will feel. Now, let's say here's something important to note though. You remember how we studied the barometer and the manometer? So in the barometer here we have a vacuum, right? Hold on. Just recapping this. Wait, manometer. We studied manometer, not barometer, no? Okay, my bad. Yeah. So it's a glass tube open at both ends, and one of the ends is connected to pressure that you want to measure, or like basically there's a pressure difference on the two ends. So one common iteration is to to have this open to the atmosphere, and this one may be connected to a room or a gas cylinder or something like that, just to measure the pressure. Now, what happens is, let's say this is a gas cylinder. Now, gas cylinder pressure will obviously be higher than atmospheric pressure. So you can imagine what started off as a liquid level like this will change, right? The liquid will be pushed down here, and the liquid levels will change, and there will be height difference. And that height difference will correspond to the pressure difference between these two sides. Not the pressure, but the pressure difference. Okay. Now, that day we did an example where this was given as, where the height was given as 5 centimeter. The density of the liquid was given as 400 kilograms per meter cube. And what else is given? Atmospheric pressure. 1 into 10 to the power 5 Pascal. So, yeah, this height difference corresponds to the pressure difference between these two sides. So, the pressure due to the liquid, that's 0.05 times 400 times 10. That's H in meters, rho in, so that is density in kilograms per meter cube, and gravity. So once you calculate this, you can figure out how much higher the pressure is on this side, because you just take this amount, which is very small amount. In fact, it's 0.05 times 400 times 10, which is 200 pascals. So this side is 200 pascals more pressure than the other side, right? Okay, let me ask you a question. Does it matter what shape a container is, or is it, for example, if I have a vase like this and another one which is like this, full of water. Yeah, if I fill this up fully up to the top, is there a difference in pressure? Pressure here and pressure here, Abhilash?
Sir?
Now, if you have two containers, one like this, one this shape, right? So you fill them up to the top. I'm asking, is there a difference in pressure at this point and at this point, or is it the same pressure?
It's a difference.
How come now? What are the factors that the pressure depends on? The pressure due to a liquid. Can you recall the equation? We used this last time on Friday. It's
So force over area?
force over area is solid pressure. Liquid pressure.
Height difference into density into G.
So then you see.
So it's a difference.
No, it's not different, because this height, the depth of the liquid is the same. In fact, this is a very funny thing, because you can have, you know, in Sri Lanka there are quite a few dams, no, with a lot of water behind them near the hydroelectricity plant. So imagine now, this thing is full, right? There's water up to here. There's water up to here. So there's a huge pressure on the bottom, because there's a very large height. No? So with the height, the pressure due to the liquid will increase. Now, did you know that it is enough to have a liquid layer like this? This liquid layer even can be responsible for the same pressure. You don't need to have all this bulk here. So even a thin sheet of liquid will have the same exact pressure at the bottom. That's quite an interesting phenomenon. Now there's an experiment that I came across on YouTube to investigate how just height affects pressure. I'll load that up now. Pascal. All right, got it. Okay.
Today we're going to do an experiment to demonstrate Pascal's law. I'm going to try to break this using just this amount of water. Who is a little bit skeptical? I know there's some. Okay. How many people here believe?
Right. Now she's trying to break that thick thing with water coming through a tube. Now you have to realize that it doesn't matter what the shape of the object is. Even a thin tube that high can carry massive pressure. Let's see.
That this is, like, really believe that this is going to work. Let's see who wins, Katerina or the barrel. But wait, how did such a small amount of water?
Now this is quite a long video, so we'll blaze through that. Now, yeah, this is all about how the pressure increases as you go deeper and deeper, right? So you can see the arrows increasing. So this is that example. The film of water here. This entire bulk of water can be replaced by a thin sheet, and it will have the same pressure. So what they're trying to say is this thin tube, they've run it up to the, apparently 150 feet. That's about like 10-15 floors. So then you can utilize that massive pressure and do it. Now this experiment was suggested by this guy called Blaise Pascal, after whom the pressure unit is named. Let's see. So then clearly, if you have height, you have pressure. End of story.
How did that jar break when you pull that with the long tubes?
Sorry?
So how did that big beaker or that tube
No,
broke?
that's the thing. Now imagine. Now 150 feet is about 50 meters. You know how long a pool is now? 50 meters. So imagine that, right? Under a pool, 50-meter high tank of water. So the pressure here is 50 meters times density of water times gravity. That's about 1, 2, 3, 4, 5 zeros to 500,000 pascals. Even if you have a thin tube, right? Even if you have a thin tube, that height at the bottom, the pressure will still be 500,000 pascals. So they broke that vessel by not using a large amount of water, but a small amount of water taken up. All right. So it had the same pressure as a huge tank of water. So using that large pressure, now the glass can withstand a certain pressure only. Yeah, that's how it goes. Okay, let's do.
So why do you multiply by 1000 into 10, sir? 15,000 that comes for pascals.
Sorry.
So why do you multiply like 15 to 1000 into 10 that comes?
The pressure due to the liquid is equal to height into density into gravity, right? So that's like the 50 meters height density of water is 1000 and gravity is 10. You don't have to memorize this, it's given in the paper.
Okay, sir.
Yeah. All right. So yeah, let's do some questions on pressure now and see how these skills apply. This is we are gonna go with physics and maths tutor for this. I'll send you the link quickly. Sure. Wait. Sorry. This is annoying. Okay. No, different website we're gonna have to use. Pressure. All right. Here we go. I'll send you a link. See whether this works. Yeah. Check whether that link works, please. Okay. Anyway. No, let's go with my screen, okay? So the starting question. Here this diver works in the sea on a day when the atmospheric pressure is 101 kilopascal. That's 101,000. Density of the seawater is, you see how it's all of it's given. Then now this question we can't do yet because we have not done gas pressure, right? Let's see this. The equation linking. Yeah. You can write that pressure difference equals depth into density into gravity. And here they ask you to find the increase in pressure when the driver descends from the surface to a depth of 11 meters. Now, if you have the paper, you can get these values and try. Shall we try? 11 meters. 11 meters, and this is the data. Just run a calculation on the calculator. H rho g, no? So H into rho is 1028, gravity is 10. We have a pressure difference of 113,000 pascals. Are you getting that? Hello?
What was the height again, sir?
11 meters. The diver descends from the surface to a depth of 11 meters.
So what was the density, sir?
Density was 1028. Then you are getting an answer of 113 kilopascals, I hope, or 113,000, right?
Yeah.
Now, here's the thing. That is the pressure due to the water only. Now you have to realize that. Hold on. Now let's say the diver is over here, right? And you know, yeah, he's 11 meters below the surface. So, but even if he was at the top, there would still be a pressure acting on him, right? Because you have to realize that the atmospheric pressure is acting anyway. So atmospheric pressure here is, they have given here, that's 101,000. 101,000 pascals. So now, on top of that, when you go down, there's additional pressure due to the water, right? So because of this, you have to add, if you want the total pressure at the bottom, that is the answer you get here, the pressure due to the water plus the pressure due to the atmosphere. Now here you got 113,000 and this is 101,000, so you'd have to add them together to get the the total pressure.
So how much was the air pressure, sir?
This one 101,000. So then together it will become 214,000 when you add them together. The total pressure is 214. Okay. Then here, these are some basic stuff, right? So complete the patterns of the water. We did this in class. The hole in the bottom will shoot out water the furthest, right? So explain the pattern means, because now the pressure is higher, the pressure is proportional to depth, and as depth increases, pressure increases. Therefore, the bottommost hole has the most pressure there and thus shoots out the water at the higher velocity, right? Then again you have this. Did we write anything about this? I think so, but wait, I don't exactly remember.
So we didn't.
You did, no? Equal in all directions, independent of container shape. Yeah. So now here, if the water level is here on this part of the flask, then since there's a connecting tube, you see, now pressure here, there will be a pressure, okay, at the bottom along that line. Now the pressure at the middle of the tube will be equal, because if there's a difference in pressure, what happens to the liquid? That's a serious question. If there's a difference in pressure, what happens to the liquid, guys? When you open the tap, why does the water come out? Because the pressure in the tank of the water company is higher than the pressure at the outlet of the tap, right? So when there's pressure difference, there's a flow. You should know this from other subjects also, like geography, because when there's a pressure difference, that's what causes wind and all. Now, the reason that the liquid level becomes same is because pressure in the bottom tube must be equal. And since pressure is proportional to depth, and there's a common, connecting tube, each one should have the same pressure at the bottom, right? Now, reason I'm going over this kind of fast is because I have allocated separate time to do mixed pressure and density revision. I just want you to appreciate the HOG and the total pressure thing, right? Now here there's another example. In a washing machine, a pressure switch is used to control the flow of water. The water pushes on a flexible container and compresses some trapped air. When the pressure of this trapped air reaches 104,000 pascals, the pressure switch turns the water off. The pressure of the trapped air is given by this relationship. Pressure of trapped air equals atmospheric pressure plus pressure difference caused by water. Can you see this same relationship that was there in this situation? There's a pressure due to the water and the total pressure. Total pressure means pressure due to water and the atmospheric pressure. So similar thing, right? You have to use this thing. Anyway, now I think, wait a second. Yeah, so we can now broadly start to talk about the properties of materials as well. Since now is the idea of fluid pressure becoming like digestible? Basically, deeper you go, the more the pressure is. Now, there's an interesting question though. After fluid pressure, you can, and we have barometer also to study. Let's study barometer today. Write them on, please. Oh. Barometer. This is like a manometer. So this is like a manometer, but the difference is that you use mercury, and this is a vacuum. A vacuum is where there is zero pressure. So the pressure equals 0 pascals. Now, on the other hand, here, this container is open to the atmosphere. So there's atmospheric pressure here. So in this case, what will happen is, because there's a vacuum up there, this is the same as you sucking a drink out from a straw, right? Pressure is actually one of the more fascinating things in physics. You can use it to climb buildings. You can use it to yeah. Now it's the same thing as if you know, you are sucking liquid out of a straw. By you create a suction here, a low pressure zone. So and here you have atmospheric pressure. Therefore, the water flows up, right? Because this push is more than the push here. So it all flows, right? The pressure causes the liquid to go up. So similarly here, this is better than any person using a straw, because it can create almost 0 pascals. So the rise of the liquid is purely due to that pressure difference. So that is the pressure equals H rho G, and that is actually equal to the atmospheric pressure. It's usually we say pressure difference. So in this case, it's atmospheric pressure minus 0. So actually, it's just atmospheric pressure. Huh?
So is that PATM?
Yeah, pressure of the atmosphere.
Okay.
Hold on. Where is my... All right. Finish. Sorry, I forgot to ask also. Finish writing, right? Or do you want me to?
So could you wait a second?
Sure. Hydraulics. That's pressure, density, and hydraulics. Arrangement and motion of particles, right?
So I can't see the lower part.
No. That's just for me.
Ah,
implications of pressure, which is after this. Okay, done, right? It's literally a glass tube and some kind of pan on which it's submerged, and then you see how much goes up, right? Now to create a vacuum, it's not difficult, you know, it's actually quite easy. All you do is you fill some mercury in a test tube, right? Right up to the top. Like this, you have to fill it right to the top. Then you have to put it in in another vat of mercury and turn it over quickly and lift it out. You don't need any specialized machinery to do this. And there is a pressure experiment that I really wanted to try for a while. I actually wonder whether it works. Like I saw it on YouTube. You have to take a bottle, fill it right up to the top, and then put a piece of tissue paper. And when you turn it over, the water doesn't go out. Have you seen that experiment? Something you can try at home, right? Finish it. Then there is another one where you fill a glass up to the top, put a piece of like cardboard on it, reverse it, and let go, and the water will stay in there. Have you seen such a thing? Go on. Sanaya, have you seen that trick being done?
No, sir.
No? Let's see. Anyway, sorry, let's not get too distracted here. So first, we'll do the necessary thing. Yeah, examples of pressure. Examples of pressure. Number one is altitude. That means air pressure. Air pressure at high altitudes. Now, you know what altitude means? So it's how much high you climb above the sea level. When you climb mountains, you increase your altitude. Now imagine a person here and a person here. I think we all kind of have heard that as you go higher, the pressure decreases. No? But how come? Usually we say when you go deeper, right, that the pressure increases. So what you need to realize is, if the Earth is like this, the atmosphere, I'm exaggerating, of course, the atmosphere is extremely thin compared to Earth, but you see, this is the mountain there, no? Right? This mountain on the Earth, it's like that. So the air is like a sea flowing on the Earth. So in that, now we are breathing, and what we are living in is, it's a fluid thing, many kilometers deep. You know that, man? Because that pressure is very, very high. So you can see that compared to this guy, compared to A, B is at a lower depth in the atmosphere layer, right? It's like he's deeper now. In fact, you know, Netflix has this like interesting TV show. It's about extraterrestrial life, right? So they imagine a planet where the gravity is so high that the density of air is thick enough to like swim in. So there are like fish-like animals which can use that denser air. It's very cool thing now. Just because on Earth air happens to be very much intangible. If you move your hand through, you don't even feel it. Feel that it's there. But
So I tried to open the folder in chat, but it says forbidden 403.
forbidden.
Yeah, so it says forbidden 402, 408.
Okay, hold on. You can get them from this link. Right? I've sent a new link. You can get it from there. But anyway, now please draw this and write person B is deeper. No, is at a greater depth in the atmosphere. At a greater depth in the atmosphere. So, since pressure equals H rho G, rather the pressure is proportional to depth, right? Pressure is proportional to depth. B experiences a higher pressure. Okay. Another very interesting example coming up. Quickly write this. Now I need to find out what the surface skin surface area of a human is. .5 and
Should we draw that circle also, sir?
sorry?
Should we draw like that atmospheric circle?
Yeah. Now this is actually, if you want, I can exaggerate it even more. Okay, this is the Earth, and around the Earth there is an atmosphere layer. In that atmosphere layer, only this mountain is, right? Right. So there is a depth. That's your H, right? Those who finish copying early, you can calculate the force acting on a human being due to the air pressure of 10 to the power 5, like atmospheric pressure of 10 to the power 5 10 to the power 5 pascals. The human skin area, you can Google and get. When I Google, I get a value of 1.5 to 2 square meters. We'll go 1.5 or any value that you like. So the force acting on us. These are crazy numbers, huh? When you crunch the numbers.
Yeah.
Sam noted. Yeah, so anyway, you guys, yeah, Oneli?
So like a baby would experience a lot more pressure than an adult human because their surface area would be
No.
less.
No, it's not like that.
No?
At a certain depth, okay, the pressure is same. So baby and an adult will experience the same pressure, but they will have totally different force on them. the pressure is equal now. E equals FOA. Pressure is a constant at a particular depth in the atmosphere, or if the baby and the adult like go for a diving, like if they dive in the sea also, at the same depth, they will have the same pressure. But the force will be different now. Force is pressure into area. And if the atmospheric pressure is 10 to the power 5, the person has an area of 1.5 meters square. When you multiply this, you get an absurd value. This is 150,000 Pascal. 150,000 newtons. For perspective, that's like if you had, that's about the weight of 3 cars. How about that? It's about the weight of 3 cars on you. That's 15,000 kilos, right? So these numbers we are dealing with is, I mean, they are insane, right? And we will explore those in more detail next time. So I'll get that down. We'll discuss hydraulics and pressure on glass. You guys just write this for today. Hydraulics, pressure on glass. Yeah, this is the way that particular aspect of pressure will be explored. But I need you to realize that if you crunch the numbers right now, there's 150,000 newtons pushing you from every direction due to the atmosphere. Okay, right. Anyway, write that down, then we'll end.